today. We're going to do 13.5 and maybe 13.6, neither of which is that great. Okay, so 13.5, linear surfaces in R3. It's not particularly deep. One starts off the following question: how does one describe a line? How does one describe a line? How does one describe a line in R3? Did I hit the record on that? I don't remember. Okay. So how does one describe a line in R3? So, you're in space, right? You're in R3, and you have some point, x naught, y naught, z naught, right? And there's a line that passes through that point called L, say. And suppose you know that, suppose you have a point, and suppose you know that V, you have some vector that is parallel to the line. Okay, and you'd like to describe that line. Okay, so that is, you'd like to describe, so you want to describe or characterize all points x, y, z that lie on the line. Right? You want to say you want some way of describing every point x, y, z. So this is like your arbitrary point on the line, and you want to be able to say that it is on the line or it's not on the line. Okay. So what kind of points lie on this line? If you have, how would you describe it? Well, one way is to say, well, look, whenever I have a point that's on the line, if I look at the vector going from here to here, then that vector is going to be parallel to this vector, right? It's going to be parallel to L, right? V is parallel to the line. We're given a point on the line. We're given a vector parallel to the line. Okay. If we take any other point on the line, well, the difference between those two guys is going to be parallel to V, right? In other words, so so that's our observation. So observe if x, y, z is on L, then the vector x minus x naught, y minus y naught, z minus z naught is parallel to this vector v. Sorry, let me give v a name. V I'm going to call ABC. Okay. So v is the vector ABC, parallel to this vector ABC. Okay. So that is to say, i.e., equals some multiple of ABC. Right? Because being parallel means that you are equal to some multiple. Right? Right. Okay. So that's the first way of describing it. That gives the vector. So we have the vector equation of L. X, Y, Z must be x naught, y naught, z naught, x naught, y naught, z naught, plus t times ABC. Well, you missed the most exciting thing. The naming game. People hit each other.
Wow.
And now everybody knows each other's names. Okay. Yeah. So this is one way of describing it, right? X, Y, Z must be x naught, y naught, z naught plus some multiple of t, some multiple of ABC. So Flo, we're talking about how do you describe a line in space?
Okay.
Okay. And the information you're given is one point on the line and one vector parallel to the line. Okay. So here's the point on the line. Here's the vector ABC parallel to the line. Okay. And you notice that if you take an arbitrary point on the line, then the difference is going to be parallel to ABC, right?
That makes sense.
Right. So this is going to be, so the difference is going to be parallel to ABC. In other words, a multiple of ABC, right? And so that gives you this first form of the vector equation in the middle. Okay. Okay. So that's the so-called vector equation form. There's also something called the parametric form. Parametric form is exactly the same thing, but you just write it component-wise, right? That x must be x naught plus ta, y must be y naught plus tb, z must be z naught plus tc, right? For some t in the reals, right? And that's another way of describing exactly the same line. Okay, so it's basically just a matter of recognition, right? If you see something like this, you say, oh look, this guy goes through ABC, and this guy goes through XYZ, and is parallel to ABC, right? If you saw something like this, it's more explicit here. It's maybe clearer to see here, but it's pretty clear here. Right? When t is 0, you see that x is x naught, y is y naught, z is z naught, and you see that as t goes, then you're adding on multiples of ABC. Okay, as t changes. Okay. So that's the parametric form. There's this other thing called the symmetric form. That is, you write it like this: x minus x naught over a equals y minus y naught over b equals z minus z naught over c. Okay. That is, you solve for t in each case, and then you say, well, look, these things all must be equal, right? Right. But again, it's sort of clear that this guy runs through, at least it's clear that it runs through x naught, y naught, z naught, right? And this ABC on the bottom this A, B, and C are the components of the vector which is parallel to the line. Okay, so there are these three ways of describing lines. Okay, not particularly exciting. One comment about the symmetric form: if for example a equals 0, then you can't. Then it doesn't make sense to write x minus x naught over a, right? Because you'd have a 0 there. In that case, right, x is fixed as x naught, right? One would write one writes, then you just say x is x naught, and then the other two are as before. So in the symmetric form, if you happen to have one of the components is 0, then you just say x is x naught, right? Because x is x naught. Okay. So sort of loath to even ask you to do an exercise on this, but I'll do it. So just take 30 seconds. I'd like you to write down some equation for the line through some point 1, negative 1, 1, and parallel to x plus 2 equals y over 2 equals z minus 3. Okay, that should take you 5 seconds. 4, 3, 2, 1. Okay, so what's one expression for it? Right, it's parallel to this line, what vector is parallel to this line? Give me the vector. Give me a vector that's parallel to this line, this second line. Well, this is a symmetric form. The vector is going to be, Sydney?
1, 2, 1.
1, 2, 1, right? Because you have A, B, C. Right? So, so it's through this and parallel to the vector 1, 2, 1, and then you just write it down, right? It's going to be x, y, z has to be 1, negative 1, 1 plus multiples of 1, 2, 1. Okay. So pretty dull. That's about as hard as that gets. Okay, so another not particularly exciting but somewhat useful trick is parameterization of line segments. Okay. So you have if you have R naught a vector and R1 another vector, and you'd like to parameterize a vector that, you basically like to parameterize a vector that starts from here and then ends up here. I'll show you what I mean. So take a look at this thing. So R of t is 1 minus t R naught plus t R1 as t ranges from 0 to 1. Okay. Okay, so let's just think about what this thing is. It's a vector, it's a function that spits out a vector. Okay. It's a function that spits out a vector, and the vector it spits out at time 0, well, R of 0 is going to be the first guy plus 0 the second guy. So at time 0, it spits out this guy. Okay. And then at time 1, you see what it does, right? It'll give you the other guy. Right? And in between, it linearly morphs, basically, from one vector to the other vector. Okay? So this guy, right, it starts here, and then as time goes on, it goes like this, and then at the end of 1 second, then it has ended up here. Okay. So this is a parameterization. You could think of this as a parameterization of the segment, or you think of this as a way of morphing one vector into another vector in a linear fashion. Okay. Laura, is it okay?
Yeah.
Okay. Okay. So this is sometimes handy. Everyone all right? Okay. Okay. Something a little bit more exciting, but still probably within the realm of boredom, is describing a plane in R3. And here is what you're given. You have this plane, and you're given a point on the plane. We'll call the plane pi, p for plane, right? You're given a point on the plane, and you're given a vector that is normal to the plane. Okay, so you've got this plane, and you've got this vector that's sticking out perpendicularly from the plane. Okay, so x naught, y naught, z naught is here, and n is this vector ABC, which is normal to the plane. And normal in this case means perpendicular. Although you recall that earlier we used the term normalized to mean of norm 1, that is of magnitude 1. That's a different use of the word normal. So normalized means that you take the vector and you divide it by its magnitude to get a vector of size 1. here, a normal vector is a vector that's perpendicular. It's just the fault of English. The English language normal actually means perpendicular. Okay. It's just a coincidence. Okay, so again, the game is, how do you describe an arbitrary point that lies on the plane? Right. And how would you? Given what we said before, how we describe the first guy, how do you think we're going to describe, given how we describe the lines, how do you think we're going to describe the planes? Well, suppose we look at the difference, xyz minus x0 y0 z0. What can we say about that difference? We get, if we look at the difference, which gives us this vector here, what can we say about that vector? Lily?
It's perpendicular to n.
It's perpendicular to n, right? No matter what xyz we choose, as long as we're on the plane, then we're going to end up with a vector perpendicular to n, right? Right? Any point that I choose is going to end up with something perpendicular to this normal vector, right? Because n is perpendicular to the whole plane. Okay. So that's our observation, right? Given any xyz on the plane, x minus x0, y minus y0, z minus z0 is perpendicular to ABC. Right? In other words, right, A times x minus x0 plus B times y minus y0 plus C times z minus z0 is what? Zero, right? It's zero, right? Because that's the dot product, right? The dot product of this guy against that guy, if they're perpendicular, is zero, right? Okay. So that guy, right? So this gives us an equation, and conversely, if you get some vector, if you end up with a vector that's perpendicular, that means that the point was on pi, right? So and conversely. If you end up with a vector that's perpendicular, you must have a point that's on your plane. Right? If you have a point on the plane, you end up with a perpendicular vector. If you end up with a perpendicular vector, you must have your point must lie on the plane. Okay. So this is called the scalar equation, right? This is called the scalar equation. Don't worry about these names. So this is the scalar equation describing the plane through x0, y, z0 with normal vector ABC. So again, it's just a matter of familiarity. Whenever you see something like this, then you say, "Oh, look, I see that the coefficients of x, y, and z give me the normal vector to the plane that we're describing, and we see the point that it passes through easily." One could also write it as follows: ax plus by plus cz is equal to b. Okay, where d is abc dot x naught y naught z naught. Okay, so that's another way of writing it, but I think this way is clearer because at least then it's completely obvious what x naught y naught z naught could be taken as. In this one, I mean, the thing is that there are infinite number of x naught, y naught, z naughts that are possible, right? So this one is maybe more honest because it's not specifying one in particular. It's not, there's nothing particularly special about this x naught, y naught, z naught that we chose. We could have chosen this one, right? So maybe this one is more, this form is more honest because it doesn't specify a point, but this one's easier to deal with because it does specify a point. Okay. So this is how one. These are two ways of describing a plane in space. Okay. And the typical sorts of exercises are as follows. So typical exercises. One, given 3 points on pi, find an equation for pi. 2, given 2 planes, find the angle between them. Right, 2 intersecting planes. Find the angle between them. And the third type of problem, given 2 planes, find the line of intersection. So let's just think about these types of problems for a second. If somebody says, here are 3 points, tell me the plane that goes through those 3 points, right? How would you do it? How would you do it? Everybody think for 10 seconds, say. Sydney, go ahead.
Using the 3 points, I would create 2 vectors.
Mm-hmm.
And then find the vector perpendicular.
By. How do you find a vector perpendicular to 2 other vectors? By using cross product. You cross them and you get a vector perpendicular.
And then I would know the normal vector, and
exactly.
then I would use the equation for ax plus by plus cz equals d by plugging in one of the points as x, y,
Sure.
and z, and then solving for d.
Okay, that would work, right? So you have 3 points, right? You have 3 points. You create 2 vectors, cross them, you get the perpendicular. That perpendicular is going to be normal to the plane. And to specify the plane, you need this normal vector and a point. Well, you have at this point the normal vector and 3 points, so that's more than enough. Okay, so that's easy. Given 2 planes, find the angle between them. So 2 planes, they intersect. Well, they're going to make some angle. So if somebody gives you 2 equations of planes, right? Say, right, x plus y plus c equals 1, x minus y plus c equals 1. And says these guys intersect, these guys obviously, these guys intersect, and so how do you find the angle between the 2 planes? Flo, go ahead.
I would describe a vector on each plane,
Okay.
and then take the dot product so that I would get the the angle between them.
Right.
From there.
Yeah, right. Because if you have the description here, well, then you know what the normal vectors are, right? The normal vector to this guy is going to be 1, 1, 1. The normal vector a normal vector to this guy is 1, negative 1, 1. Right? We know, given the description, we know what the normal vectors look like. Right? So you have the plane, and you know a normal vector to one guy. You have this other plane, right, that passes through it, right? And you have the normal vector to that guy. Well, the angle between the normal vectors will give you the angle between the plane, right? Between the planes, right? So take the dot product of these guys and then use the cosine formula, right? The cosine, recall, is going to be the dot product over the product of the magnitudes. Okay. Okay. Any questions? Any questions? So we're not gonna do it out because it's just busy work. The last one. Given two planes, determine exactly the line of intersection. Right. So you've got again two planes, right? They're intersecting. Right, got L1 and L2, right? And you'd like to find this line here, right? This line that goes up. This one's a little bit trickier, but still not impossible. So given the planes, right? One thing you do have is a normal vector for each, right? You've got one guy that's perpendicular to this guy, and you've got the other guy that's perpendicular to that guy. Right? Okay. And you're trying to find the equation of this thing here. Anyone see how to do it? Other than YouTube? Sydney, go ahead.
Okay, I think this might be a different method than you use, I guess. But like, what I would do is just take the two equations of the planes.
Okay.
And then by scaling and like subtracting them. Like,
oh, okay, sure.
Isolating variables to write in symmetric form.
Okay, so you could basically solve the two equations simultaneously, right? So that's what you're saying. Solve the equations simultaneously. That will do. Is that what you were going to suggest, Paul?
Yeah, I was going to suggest setting the equations equal to each other.
Yeah. Okay. So so you could solve the equation simultaneously and get the equation of the line. A sort of cooler way. So that's what I would have done. But a cooler way is to take the cross product of these two vectors. Say, if you take the cross product of the two vectors, you're going to get a vector that's parallel to the line, right? Because you'll get a guy that's parallel. You get the guy that goes like this. It'll be parallel to the line, and then you see that's the problem with this method is that you have to guess a point on the line. So in some sense, you have to solve the two equations anyway. So maybe this way is not that great, but anyways, it's sort of cool. The book gives this way: guess a point on the line, which is not that hard, and then take the cross product of these normal vectors, and then I'll give you the point and the vector perpendicular. The cross product of the two normals will give you a vector parallel to the line, and then you guess some point on it, and then you can go from there. Okay. Anyway, so that's that. Okay. So let's go on to let's go on to 15.6. So 15.6 is sort of I sort of feel like this is an anachronistic section in that it is talking about graphs of quadric surfaces. So graphs of equations. 15.6 graphs of quadric surfaces. So you have some equation, and you want to see what that equation, what the solution set looks like in R3. Okay, so one starts off with some simple things which are called cylinders. Well, these cylinders are really just two-dimensional things extended into three. Okay, so here is sort of a simple one. So examples of cylinders. x squared plus y squared equals 1 in R3. Okay. So what does that say? It says that the z doesn't matter, right? Z could be anything. Okay. And so you say, well, when z is if I look at this object when z is 0, let's say that z is this one. If I look at this object when z is 0, what I see is a circle in the xy plane, right? A unit circle in the xy plane, right? When I slice this object at height z equals 0, right? What I get is this thing, right? When I slice it at any height, z equals 1, right? I see that I get a circle, right? So what this object is a tube, right? It's a tube, a circular tube. A cylinder, what's called a cylinder. Okay. When the book uses the term cylinder, they don't mean cylinder in the sort of vernacular sense, but rather just a two-dimensional object that is extended perpendicularly, in both directions. Okay. Along the same lines, x squared over 4 plus y squared over 9 equals 1. Right? What's this? Anybody recognize it? Yeah, it's an elliptical cylinder, basically. Right, so in the x direction, you're going to have the minor axis. In the y direction, you have the major axis. Right? So it's this thing like this, and then extended up and down. Right? So it's you have this oval going up and down. Okay. Blah blah blah. You could have it in the xz plane, right? If your y is the thing that's left out, then right here's x, here's z, right? It's going to look like this. It's going to look like this, and extended, in this direction. Right? So you've got. It's going to go along the y-axis, right, into the board and out. Okay, not particularly exciting. Okay, maybe slightly more exciting. Quadric surfaces. So if I write down something like this, z equals x squared plus y squared plus 1. Let me just write it like this. X squared plus y squared first. Okay. What does this look like? Z is equal to x squared plus y squared. Okay. So z is always positive, you see, right? Because it's x squared plus y squared. So those things are always non-negative, right? And one way of thinking about these guys is to just slice them at particular heights. You say, I'm going to slice this thing at z equals 1, right? What do I get? Circle of radius 1, right? So at height 1, I'm going to get a circle of radius 1. At height 4, what do I get? Circle of radius 2, right? So the radius increases. Right? At height 9, again I increase by 1. Okay, and down at the bottom, right, at height 0, I get the point 0, 0. Right? So this is at z equals 1, z equals 4, z equals 9. I see that I get circles of linearly increasing heights, right? Radius 1, radius 2, radius 3. Right? And so if I slice this thing vertically, right, at say y equals 0, what do I see? Well, if y equals 0, then I have z equals x squared, which is a parabola, right? So I'm going to see a parabola. Right? And that's what I see. Right? This thing is a parabola that has been spun around to make circles. This is what's called a circular paraboloid. Okay. If I had something like this, z equals x squared plus y squared plus 1, what do I get? What's the difference? Peter?
Just shifted up.
It just shifted up 1. Okay, so same thing, just moved up 1. Okay. What if I have something like this? Z squared is equal to x squared plus y squared. Z squared is equal to x squared plus y squared. Okay. In that case, the height z, at height z, what's going to be the radius of my circle? You have circles again, right? At each slice you have circles. But at this time, at height z, what's the height? What's the radius? Who said it?
Z.
It's going to be z, right? Right. So at height z, we're going to have radius z. Right? So this time, it's not going to be a paraboloid, but it'll be what? The radii aren't increasing in a parabolic way, but just in a linear way, right? At height z, at height 1, the radius is 1. At height 2, the radius is 2. At height 3, the radius is 3. So what do you get? You get a
Straight line. Straight line.
straight line, right? So you get a cone, right? You get a right cone, right? On top and bottom in this case, right? Because z could be negative now. Okay. Yeah. So, I'm not sure. So, if I have something like this, z squared is equal to x squared over 4 plus y squared over 9. What do you get then? Well, at each height z, you're going to end up with an ellipse, right? You end up with an ellipse. So here it's just going to be a point. At height 1, you're going to end up with this standard one. 3, 3, right? And then they're going to, I can't really draw it, but you basically get ellipses going up, and then ellipses going down. This but expanding in a linear manner. Okay, so this is what's called, I can't draw it, sorry, but it's an elliptic cone. Okay, so if I looked from the front, I would see one cone. Right? If I look from the side, I see another cone of a different aperture. Right? I would see a wider aperture cone like that. Okay. Right? And similarly on the bottom. Right? These 4 things going out. Okay. So I don't know. Just maybe you can't see what I'm drawing here, but right? Along the x-axis, there's a narrow thing like this. Along the y-axis, there's a wider thing like this, right? So there's a narrow guy, and then there's a wider guy, and then at each height there are ellipses. That's good, I think. Okay. So so there's this whole section on these things, and they're sort of more complicated. So it's an elliptic cone. It's also called a one-sheeted hyperboloid. Right, there are all these names and things. I don't consider this section to be that important in the sense that you can always, in this day and age, you can just plug this thing into a program, and then out will come the picture. But it is sort of useful to. The skill that I'd like you to get is simply this idea of slicing. So to figure out what something looks like, slice it at different heights, and slice it, you know, with respect to different axes and at different heights, and you'll get some sense of what the thing looks like. Okay. But again, I think this is sort of an old tool, like being able to do jujitsu or something like that. Like, maybe it was useful at some point, but you know, now not all the time. Okay. Okay, so that's it for today. I do have some things to hand back, including the diagnostics.